continue, okay? So far, okay, all the matrices we talk about, okay, the elements in the matrices are real numbers, right? But starting from now, okay, the matrix that we are discussing could be complex numbers. Okay? So, again, this is very useful in the deep learning theory. Okay, so if alpha equal to a plus bi is a complex scalar, the length of alpha is given by, this is, alpha bar alpha, square root. I think you guys know this, right? 就是给定一个复数 a 加 bi， 它的那个，就是我们讲它的这个 scalar 啊，应该说 length of 这个 length of alpha， 我们是定义成 a 平方加 b 平方开根号，这个知道哦。这个复数方面的，我不知道你们有学多少，但是你们高中有学复数吗？还是有学吗 ？OK， 那这个阿尔法 bar 是什么东西？就是那个复数的那个共轭，就是如果说 a 加 ib， 它的共轭就是 a 减 ib。OK。如果我讲到这边，就 a 加 ib 乘上 a 减 ib 会变成 a 平方加 b 平方嘛？大家应该知道，对不对？然后要开根号，所以是这样子。对，那这个东西，希望大家注意一下哦。就是说这个，如果大家不记得的话，I hope this reminds you, okay, whatever you have learned about like complex numbers, okay. 所以呢 ，OK， if z equal to z1, z2, blah blah blah, zn transpose, okay, is a column vector. It's a vector in Cn. So be very careful. Okay, so here every term, every element here, zi, they are complex numbers. Okay, so as I already emphasized, okay, starting from now. Okay, the elements that we discuss, unless I specify otherwise. I mean, all the elements from now on in the matrices are complex. Okay， 就是除非我另外讲，要不然的话，这个现在讨论的每一个 element 都是复数哦，都是复数。所以像这 z 是一个这个，就是说像这样子一个 column vector。有 n 个 component， 那每一个都是复数哦，都是复数。The length of z is given by, okay, we define this length of z to be this one. z1 squared plus z2 squared, blah blah blah, plus zn squared. This zi squared is defined to be like this. So it's actually like this. It's each zi multiplied by its conjugate， 就是每个 zi 乘上它的共轭，然后把它加起来。So because it looks like this, right? So we can also write it as like this. So z bar t dot z. Okay, and like square root of it. 什么是 z bar t？ 就是你这个 z 是这个嘛，那 z bar t 就是它每一个 element 变成它的 conjugate。OK， 然后这样子，这个就是一般的那个 dot product。你可以讲它是 inner product， 或者讲说这个如果把 transpose 以后。就变成说矩阵相乘嘛，就是一个就是这个乘上这个嘛 一个列矩阵乘上行矩阵这样子，那跟那个以前讲讨论的大 product 是基本上一样的。然后这个开根号 ，OK。那 so now okay, because we see like this z bar t will be used very often and very common. So we define z bar t, okay, to be the z to the power of h. Oh, this is a terminology. OK, 就是 zh 其实就是你把 z 的每一个 component 做 conjugate 以后，把它 transpose。我这样讲大家记得吧？可以吧？好，那我今天再提醒大家一下，我们今天讨论是复数的这个情形嘛，对不对？如果说我们现在的矩阵或者说 whatever vector 矩阵里面就只有 real number， 那你做 conjugate 是不是等于原来自己，对不对？那你的 zh 就会等于什么？就会等于 zt transpose， 对不对？对，因为你那个 z bar 就等于 z 嘛。对，这边要跟大家讲一下，就是说，就是我们现在后面讨论，我们通常都是讲，比如一个矩阵，它的 h， 但是那个 h 代表就是它每一个 component 都 conjugate 然后 transpose， 但是在一些特别的情形，如果它是整个都是 real，if it's real matrix，then it's just the transpose，it's just the transpose。And also like 在前面我们讨论的一些东西，如果说是 real matrix， 然后我们你看到那个 transpose， 那我们也可以写成就是特别在 real number 那个 number 下面它是那个就是矩阵的 h， 这是让大家确认一下这个事情啊。然后就是说我们可以写成这样 z the size of z or like the length of z to be this one. Okay? So now, once we define this, okay, there are several things we can do. Okay? First, okay, so if we have a vector over, V be a vector space over complex numbers, inner product of V is operation that assign to each pair of vectors z and w, okay, in V, okay, so zw satisfying the following conditions: z dot z, okay, or z inner product z equal to 0, if and only if z equal to 0. Okay, so for all z and w in V, okay, z, okay, z inner product z greater or equal to 0. Okay. And z inner product w will be the same as w inner product z, and alpha z plus beta w u will be alpha z u plus beta w v w u。所以我们有这个东西哦，这个是我们的那个 complex 的这个 inner product 的定义。那其实，如果你对这种什么 complex inner product 那搞得很模模糊糊，不太清楚，你就这样了解，它就是那个 a 加 bi 就是 a 平方加 b 平方，那个或者说这个它就是如果说这 inner product 自己的话，或者它就是 z， 它就是 z。zh， sure， 就 zh 这个东西的那个，我记得开根号吧。 那因为这个东西出来就是 a 平方加 b 平方嘛，对不对？当然你这边because these are vectors, so you have like a this thing, okay, for each component, okay, so you should ai squared bi squared. This is a vector, okay, and this must be greater or equal to 0, right? Because like I mean you got like the sum of the squares, they must be greater or equal to 0. The only situation for it to be 0 is a, b are both 0, right? So that's like this. Z equal to 0 if only if z equal to 0 and z, okay, inner product z is greater or equal to 0. And this one equal to, I forgot, z inner product w, it will be w inner product z, okay, with conjugate. I forgot to mention this. Okay, I mean, there should be a conjugate there, okay, because like z inner product w is like well, let's derive this one first. So u inner product alpha z, yeah, plus beta w, okay, it's going to be, you change the order, you get the conjugate at the top. So alpha z, plus beta w, u conjugate, and then it will be, you can get like this one, okay, to be this, okay, apply this one. So it will be alpha z u, okay, plus beta omega wu with a conjugate at the top, okay, and because it's a addition, so you can break it like so it's going to be alpha bar z u bar plus beta bar w u bar, okay, and then we apply this one once more, we get this one will be alpha u z conjugate plus beta conjugate u w. So that's what we want here, okay? So in reality, we can define z inner product w to be wh dot z, okay? So this is like a very, very convenient definition, and it satisfies all the requirements, okay, for the inner product. Requirement here, okay. So give an example, okay. If z is this one, w is this one, then z inner product w will be wh z. So what is wh? So it's going to be, you change each of these into a conjugate, and change this one from column vector to row vector. So it becomes 2 minus I, negative 2 minus 3I, okay, and this one, so it becomes this, okay. And z dot z, okay, inner product z will be zh. So it's going to be like just this one, okay. And the w inner product w, that's similar, okay. Not much to talk about, okay. So conjugate in the Hermitian, okay. So M is M times N matrix. So previously we talked about the vectors. Now we are extending a similar concept to matrices. Okay, so M is M times N matrix with Mij equal to alpha Aij plus Ibij. Okay, so it's obviously like this N. I mean, the elements are complex numbers. Okay, so A equal to Aij and the B equal to Bij. We have M. You can write M equal to A plus IB. So the conjugate of M will be written as M bar is A minus IB. So in other words, every term in the matrix M, if there's a imaginary part, you just change its sign. That's it. Okay. So MH is the transport of M bar. So as I said, whatever MH you have seen, okay, you first get the conjugate for each component and do a transpose. Okay? So it applies for vector, it applies for matrix, pretty much similar. Okay? So if AB is Cm M times N, okay, so they are a complex number, M times N by N matrices. And the C is N by R, like a complex number of matrices, okay. Then H equal to A, and the alpha A plus beta B H will be alpha bar AH plus beta bar BH, and ACH will be CHAH. Due to the time limitation, this is pretty much easy to verify. Okay, you just, for each AIJ, you just verify if this is the case. Okay, because like you see this AIJ, if you conjugate and transpose, and then you conjugate and transpose back, obviously they will be the same. And this one, I mean, again, you just the ith row jth column in this one will be something on the left hand side, and you can compute the ith row jth column term. I mean, from the right hand side, they should be the same, and the same thing, I mean, can be said for this one. Okay, so I will hand wave this one. I mean, I will just let you guys to verify. I mean, in the exam, if I ask you a question like this, you can do that, right? Yeah, it should be pretty straightforward. Okay. Then we can talk about Hermitian matrices. Okay, a matrix M is said to be Hermitian. What do we mean by Hermitian? If M equal to MH, so so like a definition of MH already, right? So you compute like the conjugate for each term and transpose it, right? Then okay, there are many such cases. For example, this one is one of the example. You can see if you compute the conjugate and then transpose, obviously you'll come back to itself, right? Because like you change this one to 2 plus I, change this one to 2 minus I, you transpose, it goes back to itself, right? For like diagonal terms, the conjugate, well, it will be itself. I mean, the conjugate, to be honest, if a matrix is Hermitian, its diagonal elements must be real. Think about this, right? Why? Because after transpose, like the diagonal elements stay at the same place, right? So it basically tells you, I mean, that element, if you do a conjugate to that element, it will be this itself. So what kind of complex number, if you do a conjugate, it becomes itself. It go back to itself. It must be real, right? It means like you don't have a imaginary parts, right? So that's like that basically tell you like the diagonal elements must be real. And this one, I mean, you have something similar to this one. Okay, if you have that, I mean, your matrix, I mean, is a Hermitian. And if for real number, for real matrices, okay, a real matrix, if a real matrix is Hermitian, what does that mean? That means that matrix is symmetric, right? Okay. So far so good, right? And I also want you to understand that even though we are talking about complex matrices, okay, I mean we could compute the eigenvalues. We could compute the eigenvectors exactly just like what we did previously for real matrices. Okay, the way to do it, the way to deal with the eigenvalues, exactly the same, Okay, so for example, okay, we have this theory. The eigenvalues of a Hermitian matrix are all real. Furthermore, eigenvectors belonging to distinct eigenvalues are orthogonal. Okay, so if a matrix is a Hermitian, okay, so we know like A is a Hermitian, so A equal to AH, right? Okay. So what do we mean by eigenvalue for Hermitian matrix? Okay, so it means AX equal to lambda X, right? Right? I mean, as I say, like it's a eigen the eigenvalue discussion for the Hermitian matrix are exactly the same. I mean, so yeah. So let's consider, okay, alpha equal to AXHAX. We particularly let alpha to be AXHAX. First, I want you to be aware, okay, that alpha must be just a single element, right? Of course, it could be complex. It could be complex. I mean, but at least the size must be one by one, right? Because it's like X, H, A, X. And remember, X is a column vector, right? So the X, H is a 1 by n, right? 1 by n multiply n by n multiply n by 1. So the result must be 1 by 1, right? The size, I'm not talking about the value. I'm talking about size. So alpha, if we let alpha to be this one, okay, then, okay, first we know alpha must be real. Why? because you consider the conjugate of alpha, the conjugate alpha, it will be, you know, alpha h, right? Because like, well, it's 1 by 1, right? The transpose, I mean, will become the same, I mean, the same place, right? I mean, it's only 1 by 1. So you just conjugate and the transpose, go back to itself. So alpha conjugate will be alpha h. So alpha h, so you apply the h on this one. Okay, and if you remember, here, we have this, right? So you just, so you get, you change the order and you apply h on each term. So it becomes x, h, a, h, x, h, h, right? But x, h, h is x itself, right? You go back to x. And the a, h equal to a, right? Because a is Hermitian, right? Right? So it becomes, this thing becomes this one. So this one we know is alpha, right? We define alpha to be like that, right? So the first thing we know is that, okay, the conjugate of alpha equal to alpha itself. The only case this will happen is alpha is real, right? Okay. And then, okay, alpha equal to x, h, a, h, x, okay? So I mean, for any, if x is you know, is a corresponding column vector for column, corresponding eigenvector for eigenvalue lambda, then we put ax to be this one, right? So we can get the lambda out because lambda is you know, it's a value. I mean, even regardless it's a real number or complex number, we can always, you know, get it out of the way, right? We can put it here. So xh times x equal to this one square, right? The square of the length of x. And we know this, you know, this is the real number. This is the real number, right? So it forces lambda to be this one, which must be a real number, right? So far so good?可以吗？只听到人打喷嚏，都没有人讲说有没有问题，对啊，应该还可以嘛，对不对？就是这个证明里面，唯一可能你们比较不会想到的是，怎么样让阿法等于这个啦？这一块是要一些要一些知道怎么讲？要一个比较 tricky 啦，要一个证明的技巧，其他的其实都蛮 straightforward 的。OK， 好，然后再来另外一个部分，就是 another thing is okay, I mean we say like the different eigenvalue, the eigenvectors for different eigenvalues are orthogonal. Oh, by the way, I mean we can also define orthogonal. I mean the same way as we defined for like the real vectors. Okay, what's that? It's like the inner product of these two eigenvectors is 0. Okay, so if the inner product of two eigenvectors is 0, then that means these two eigenvectors are orthogonal. Okay. So, okay, if x1, x2 are eigenvectors belonging to distinct eigenvalues, lambda 1, lambda 2, then we consider this AX1 HX2. Okay, AX1 HX2. So this one, okay, if you apply H on this one, it becomes X1 HAHX2, right? And because we know like the A is Hermitian, right? So AH equal to A, right? Okay, so in our this AX2 will be lambda 2 X2, right? So you can put lambda 2 in the front and X1 HX2, right? Okay, and then AX1 HX2. I mean, we can apply like this one. We can get like what should we say? Like we can make the whole thing an H, and apply H inside here, so it becomes X2H, and then this one H and H, so it becomes AX1, right? Then we know like this one, okay, this one will have lambda 1 X1, right? So you see, we get like a lambda 1 X1 HX2, right? So this one and this one, they are the same, right? So one give us this, one give us this. Okay, so what does that mean? Because like lambda 1 and the lambda, these two are of the same value, right? But we have two different factors, right? So the only case for this to be, I mean, to make sense is this X1 HX2, or the X1 X2 inner product of X1 X2 is 0. Okay, so in other words, they are orthogonal. Okay. Again, I mean, really, like the technique used here is this thing. You need to know how to write this. Okay, once you know how to write this, I mean, the rest becomes tricky. I mean, it becomes like a trivial. Okay, but yeah, it takes some effort to get the idea. Okay, how to do this type of proof. Okay, but yeah, I mean, well, that's like I mean, why we need to discuss this today. Okay, and then the next one is unitary. Okay, an n times n matrix U is said to be unitary if its column vectors form orthonormal set in Cn. So its column vectors are not only orthogonal, they are orthonormal. Okay, so I mean, every pair of them, the inner product is 0, and also every one, okay, every one of them, like the length will be 1. Okay, so if this is the case, we know UHU is identity matrix, right? Why? Because if this is U, we know each of them, like as I say, like each pair of them, the inner product is 0, right? And each and each of them, the size is 1. So what is UH? UH is this one. Okay, if I write it is as a x x1 xn, so it becomes this, right? This one is x1 bar, right? Xn bar, right? Right? You get a, because this is like a UH, right? What is H? It means like you make each of them, you just convert each element into a conjugate and then do a transpose, right? So this is conjugate, and you change from the column vector to row vector, and you can see that if you do this, the diagonal part will be this one times this, for example. So it will be like each diagonal will be xi h dot xi, right? So that's like it should be like this. Should be this, right? Just xi. Okay, so it will be like a size, the square of the length of xi. Okay, it will be 1, 1, 1, 1, 1. And the other part, okay, we know they must be 0 because like in each of them indicate like the inner product of two different column vectors. Okay, and we know like because it's orthogonal, right? So we have that. And a real unitary matrix is an orthogonal matrix. This is obviously the case. I mean, everything we discussed, like in complex domain, you know, when you consider it in a real domain, I mean, it's obviously like the satisfy. Okay, so a real unitary matrix, it just, you know, it's just U transpose, right? U transpose. So it's an orthogonal. Actually, we discussed something similar to this one in the previous, I forgot it's a section or chapter, but I mean, you should be able to trace back to the previous one. I mean, it's similar discussion. Okay, so if the eigenvalue of a Hermitian matrix A are distinct, okay, then there exists a unitary matrix U that diagonalizes A. Okay, so this one is similar to what we discussed. Like which one? It's yeah. This one is actually similar to, where is it? This one. We actually prove this thing. So I mean, the idea is similar to this one. Where is it? Okay. So basically like you try to multiply this each of these eigen vectors, this is x1 xn, you get like lambda 1 x1 lambda n xn. Okay, and this one can be, I mean, if this one can be written as x, this one be ax equal to xd, where d equal to lambda 1, lambda 2, lambda n, the other are 0. Okay, then, you know, I mean, it's pretty much the same thing. So there exists a unitary matrix U. I mean, remember this x1, xn, each pair of them are orthogonal, right? Okay, and we can certainly make them orthonormal, right? We just divide their length, right? For each of these eigenvector, we just divide the length. So it's just like this is U. Okay, this is U. And we know like the inverse of U is UH, right? We already know that. So UH AU equal to D. So we have that, right? Because it's AU equal to UD, right? This is D. So, I mean, the inverse of U is UH. So UH AU equal to D. Done. Right? The idea will be very, very similar to what we discussed earlier. There, okay. So you can see that we don't even call this a theorem; it's just a corollary. 在数学上哦，顺便跟你们讲一下 ，OK，theorem 是比较重要的东西，比较大的东西哦。corollary 只是一个引理哦，就是你从上面这个 definition 你得到的一个，譬如说应该或者说从前面的 theory 你得到一个很简单的一个推论而已。所以这个是 this is actually very simple stuff. The only thing we need to make sure is like UH is the inverse of U from the previous one, and once we know that, I mean, the rest is pretty straightforward. So here we have an example. So A is this one, and by the way, I mean, if you take a closer look, A is a Hermitian, right? A is a Hermitian. So you can PA lambda, you can try to compute this one. I mean, you get like I mean, lambda to be 0 and 3. Okay, when lambda is 3, I mean, you get like this eigenvector. When lambda is 0, you get this eigenvector. So you try to compute like obviously these two, we don't even need to verify. These two eigenvectors, they must be orthogonal to each other. We don't need to verify that because we already proved that, right? But we do need to, change each of them into the unit length, right? Because we need to make a U, so we need to, divide the x1 by the length. So it's like this. Same thing. We divide like the x2 by its length, so we get this one. So the U will be, this is the first eigenvector, second eigenvector, divided by this one. Okay, so this is U. So UHAU, so U is here. So UH, you just, conjugate and then transpose. You get this. And you have another, this one. So you multiply 2 of this, you get like 1/3, right? So, and the A is in the middle. Okay, so you multiply this together, you must get this one. Okay, the diagonal terms are the eigenvalues for a corresponding eigenvector, 3 and 0. You can verify this by yourself. Okay? So I guess, let's take a 10 minutes break. When we come back, we'll continue our discussion. Okay? 好像来报佳音了。